So, in the last lecture we were discussing how to analyze experimental data with respect to the Avrami equation, where we have a set of experimental data points of the phase transformed, fraction of the phase transformed as a function of time, and based on this data one wants to determine the parameters n and k. For this purpose we had linearized this equation, the Avrami equation, and then reduced it to a simple linear equation of the form y equals a0 plus a1x, where x was simply log of the time and y was a double log of minus log of 1 minus the fraction transformed. So, we transformed the experimental data as well to these quantities that we did in the last lecture. Then x versus y, if you plot, it should come as a straight line. Now, the objective here is that we want to determine the best values of a0 and a1, which best represents a straight line through these set of points x and y. In order to do this, we will use the method of linear regression, or it is also called as simply least squares technique, and one shall see how that is done. Now, in any equation of this form where experimental data is also involved, there is always a statistical variation of values. So, such a equation is also, we add an error term to it. This error is simply a statistical fluctuation of the response y when the independent variable x takes up a certain value. This we assume that this error follows a normal distribution. The normal distribution is a bell shaped curve with mean of 0 and standard deviation of sigma. So, since it is an error term, mean is 0. So, the average of all the errors put together should reduce down to 0. Now, we wish to estimate, or the best estimates for a0 and a1, I will denote them as a0 cap and a1 cap. Once these best estimates have been made, then the predicted value of y from these estimates, we will call that as y cap, which is equal to a0 cap plus a1 cap x. Now, if this is the ith value of the independent variable xi, then this is the ith response. So, I have a set of data here x and y. So, I have x1, response is y1, when x takes up the value of x2, the response is y2, and so on. If the response of the ith value of x is xi, the response is yi, and so on up till n, if I have n data points that I have collected. Now, this is the predicted value at the ith response, and here this is the measured value at the ith value of the independent variable x that I have experimentally set up. In this case, it is log time. So, I have this, which means I can write down the difference between the measured yi and the predicted yi cap that I obtain if I have the estimates for A0 and A1. This difference is called the residual, and I will denote it as EI, which is actually related to this E that I was discussing, and this EI as well would follow a distribution with mean equal to 0 and standard deviation equal to sigma. Graphically, one can understand what is happening here. If I just plot my data points and through this data I draw the best fit line and I look at different values. Suppose this is my ith, this is xi, then this is yi, while this point on the line is yi cap or the predicted value, and this is ei, the difference between yi and yi cap. Ei will be positive if yi is above the line, the measured value is above the line. Ei will be negative, which in this case this is the measured value or the observed value and this is the predicted value. In this case Ei would be the residual would be negative. So, some of the residuals are going to be positive while the other residuals are going to be negative. So, what we do is we do not work with residual EI, but we square the residual. So, instead of, because some of them are positive, some of them are negative, if we square them then everything will become positive. So, EI square, and then I sum up all of the individual residuals from I equal to 1 to n. This sum I will call as SS, sum of the squares of the residual. So, let me just make a point here, sum of the squares of residuals. Now, and let me just further expand this. Instead of writing EI, let me write it as yi minus yi cap squared. We want to find now A naught cap values for, or the estimates for A naught and A1 as A naught cap and A1 cap, such that S sum of the squares of the residual, SS residual, is minimized. So, we need to minimize the sum of the squares of the residuals. So, how do we do this? How does? Well, its SS residual is a function of all of this. So, we need to minimize it by taking certain derivatives and setting them to 0. So, what we do, let me expand this further. Yi minus, now instead of writing yi cap, I expand yi cap as A0 cap plus A1 cap xi, and hence this will become A0 cap minus A1 cap xi. Now, in order to minimize this sum of the squares, I need to differentiate SS residual with respect to parameters A0 cap and A1 cap. So, I take the derivative del SS residual del A naught, set it to 0. Similarly, I take the derivative of sum of the squares of the residual with respect to A1 and set that as well to 0. So, let us take the derivatives now. If I first let me take the derivative of with respect to A naught. So, if I do that, and this should be square here, I look at this function and take the derivative with respect to A naught only, keeping A1 cap as constant. This is taking a partial derivative. This will become minus 2 that comes from the power, and 2 comes from the power. The negative sign comes from taking the derivative inside. Well, derivative of with respect to A naught cap would be minus 1, and hence I get minus 2 summation, and the stuff inside remember we are taking the derivative with respect to A naught and A1 and not with respect to x. This should be set to 0. If I expand this further individually, this 2 and negative sign will go, and what I will have is summation yi minus summation A naught cap minus summation A1 cap xi equal to 0. Well, A naught cap is a constant, and hence it is in the sense that this comes out of the summation, and hence this whole thing basically you are adding A naught cap n times. So, this is simply become n times A naught cap, where n is the number of data points. This A1 cap comes out of the summation and can be written as A1 cap out here. Then I can divide this entire equation everywhere by n. So, I divide this by n, divide here by n, divide here by n, and the right hand side remains 0. So, this n and this n, this n will cancel, and what I am left with is this term. What is this term? This is the average value of y. Simply add up all the y's, divide by n, giving you an average y. Similarly, this term here, summation xi upon n, is an average value of y. So, let me call this value as y bar, and let me call this value as x bar. From this, it is easy to write that A naught cap equals y bar minus A1 cap x bar. So, this is one important equation I have which relates A naught to the average y, which that is average of all the measured values, average of all the independent values that I got from the experiment, while A1 cap I still need to determine. So, that would come from this relation, that we take the derivative of the sum of the squares of the residual with respect to A1 now. When I do this, I get again differentiate, but this time I differentiate with respect to A1 cap, and I will get the following result: minus 2 summation yi minus A naught cap, and this time This minus is coming from here when I differentiate a1 cap, but I will be left with minus xi. So, minus can come out of the summation, but xi will remain in the summation, as you will see. So, let me first write down the whole thing: a naught cap minus a1 cap xi times this xi that is coming when I differentiate with respect to a1. So, xi will be left and it will be remain inside the summation. This would be set to 0. I can forget about this 2 and this minus sign and just expand this. When I do this, I will get summation xi yi minus a naught cap summation xi minus a1 cap summation xi square. Now, in order, and this is equal to 0. Now, in order to solve this, I can substitute a naught cap from this. This result can be substituted into this equation, and when I do this, I get summation xi yi minus y bar, I am coming here. So, I will get y bar summation xi, and then a1 cap will also come here. As a result, I will get plus a1 cap, and I can take this in brackets here, and I can write x bar summation xi minus summation xi square, and this is equal to 0. So, now I have an expression in which only the parameter a1 cap is there, which means I should now be able to solve for a1 cap from here, and then that value can be substituted here to get a0 cap. Now, I am not going to prove this, but it is somewhat longish, but we can show that the term here in square brackets can be written as minus summation xi minus x bar square, while the term, this term can be written as summation xi minus x bar multiplied by yi minus y bar. The way you can prove it is you expand this and eventually show that this is equal to this. Same thing you do here, you expand this and show that this is actually equal to this term. From this, we can find or write a1 cap as summation xi minus x bar times yi minus y bar divided by summation xi minus x bar square, where the summation is running from I equal to 1 to n, I equal to 1 to n. Now, just we can abbreviate this and write this expression as the numerator summation xi minus x bar times yi minus y bar. I'll write it with the symbol s xy, s subscript xy, and the denominator I will write as S subscript XX. So, this forms an important equation which from the experimental data of x and y I will get A1 cap. Similarly, once I get the value of A1 cap, I will plug it into this expression, and I know what is y bar and x bar, and hence I will get the value of A naught cap. So, these are the two best fit values of the model or the linear equation A naught plus A1 x. So, once I have this, then I will have the straight line, and I can draw the line and see how that line fits the data. So, what I will do now is actually take our data of the eutectoid steel where fraction transformed as a function of time, and see how we can fit the straight line through that data. So, now let me start to look at this data. So, I have the same Excel sheet that I had earlier, in which I had already transformed log t and log of minus log 1 minus f. So, let me I will call it as x, this is my x and this is my y, and my equation is A naught plus A1 x, and these are the equations that I just wrote down on the board. A0 is equal to y bar minus A1 x bar, and A1 is equal to summation xi minus x bar times yi minus y bar divided by summation xi minus x bar square, which I have abbreviated as Sxy upon Sxx. So, one of the first things that I think I need to do in order to calculate all this, I need to get the average y and average x. So, let me write down first the average values. So, my x bar average is simply, I can use the average function of this spreadsheet, and this 5.259 that is shown is the average of all of these values. Similarly, I will just copy this formula here, and this gives me the average of all of these y values. Now, I need to calculate S, or before I calculate Sxx, I need to calculate xi, a set of values xi minus x bar and a set of values yi minus y bar. So, let me call this as x minus x average and y minus y average. Now, this set of values would be the first x value is in cell D5. So, D5 minus the average x, and I will anchor it so that it does not change when I copy the formula. This gives me the first x minus x average value. The second, or rather the first y minus y average, the corresponding y minus y average value would be the first y value, which is E5, minus the average of all the y's, anchor it, and this gives me the first pair. Now, I just have to copy this and populate it. So, I have now I had these 5 data points. So, now I have correspondingly 5 sets of x minus x average and y minus y average. Now, let me calculate Sxx and S x y. Now, S x x is the sum of the squares of the deviations x I minus x bar square. So, this is simply equal to, there is a function called sum square. What it will do is, the set of values that are given in the arguments, each of them are squared and then summed, and that should do the purpose, because I need to square these x minus x average values first and then add them up. So, this gives me the denominator of this equation for A1, and then S x y I will get by another function in Excel, which is sum of the products of the corresponding sum of the product of the corresponding values. So, the first set of values x minus x average, comma, I give the second set, and what this spreadsheet will do, it will correspondingly first multiply this and this, add to the product of the second pair and the third pair, and so on. This gives me S x x and S x y. So, now I should be in a position to determine the parameters A0 and A1. So, let me write A0 here and A1 here, and below these I will calculate the values of A0 and A1. Well, first I need to calculate A1, then only I can get A0. So, A1 is equal to Sxy upon Sxx. So, Sxy is this E21 divided by the value in the cell D21, which is Sxx, and this gives me the value of A1, or the slope 4.953, or very close to 5. Now, I will estimate A0, which is the average x, average y, y bar, this is the equation, minus value of the estimate A1 multiplied by the average value of x, and this gives me the value of minus 26.995. Now, this is in a nutshell the method of linear regression. We will look at this method a little bit in more detail as to how good the fit is and so on, and in the next lecture. So, I will stop here. In the next lecture, I will discuss the values of n and k that I get out of this linear regression, and look at how well the data fits to the experimental data points.